360. Think of that as the ultimate guide to concrete. It's what engineers use to make sure that things don't fall apart.
Well, SOG might seem simple at first glance. It's just a slab that's sitting on the ground, right? But, it's actually deceptively complex. There's a whole lot of engineering that goes on behind the scenes to ensure that slab can handle the loads. All the different forces, the heavy loads, the forces of nature, everything it's got to stand up to.
So let's start with the basics. I mean, what exactly is a slab on ground?
So the ACI 360 defines a slab on ground as a slab that sits directly on the ground, mainly designed to support loads. It's basically the foundation and the floor rolled into one.
Okay, so that's the basic idea. But our source material actually goes on to talk about different design approaches, even comparing codes from different countries. For example, the Egyptian code ECP 203, which initially focuses on unreinforced SOGs and even gives us an example for calculating the max bending moment capacity.
Yeah, and that's really interesting because it shows just how engineers in different parts of the world might approach design from different angles. So starting with an unreinforced slab actually establishes a baseline. It's like, learning to walk before you run. And then the calculation you mentioned, that one is all about making sure that the slab can withstand the forces that are trying to bend it, trying to make it crack.
There's also this little interesting detail about the Egyptian code allowing fibers specifically for shrinkage reinforcement. It's like a little sneak peek into this bigger world of fibers in SOG.
You picked up on that. Yeah, it's an important concept because that specific mention actually hints at a key concept. Fibers aren't just about adding strength, right? They're also about controlling how the concrete behaves. As it dries and shrinks, it's about managing those inevitable cracks that are going to form over time.
Yeah. Speaking of unreinforced SOG, the ACI 360 has a whole section dedicated to its design. It seems like a really crucial starting point, even if most slabs end up with some kind of reinforcement.
Right, exactly. It's like the foundation of it all. And when designing an unreinforced SOG, it comes down to figuring out the thickness of that slab to limit stress and prevent cracking under load. And that's where that term modulus of rupture comes into play.
Okay. You have to break that one down for me. Modulus of what now?
Okay. So imagine you're trying to bend a stick, right? At some point, it's going to snap. The modulus of rupture is basically a measure of how much bending stress concrete can take before it cracks. So it's super important when you're relying on the concrete itself for strength. No rebar or anything like that.
Our source material also mentions factors of safety, which sound pretty important. And they even mention factors as low as 1.4 for some scenarios, which, I don't know, it seems a little unnerving.
Yeah. It might sound scary at first, but these safety factors are based on a ton of research and real-world experience. They take into account, the type of load, how often that load is happening, and then the consequences of failure. So a lower safety factor doesn't always mean the slab is going to be unsafe. It just means that the engineers have, carefully calculated the risks.
So it's more like a controlled risk than just like throwing caution to the wind, right?
Yeah, exactly. It's a balance between strength, cost, and practicality. You wouldn't over-engineer a garden shed like you would a skyscraper foundation.
That's true. That's true. Now, let's talk about something we can all relate to, fatigue. And I'm not talking about the kind of fatigue that you feel after a long day. I'm talking about fatigue in concrete, especially in the context of things like moving vehicles. I mean, we've all seen those roads with cracks and potholes and stuff like that.
Yeah, the constant pounding of traffic. That's fatigue in action, repeated loading like that, heavy trucks driving over and over a slab day after day. That can actually weaken the concrete over time. That's why engineers have specific calculations and design strategies to combat this, to make sure that that slab can handle thousands, even millions of cycles of those loads without failing.
The source material even gives an example of how the number of repetitions that a slab can handle changes dramatically as the stress increases. So at a lower stress level, it might be good for, practically forever, but then a tiny increase in stress can drop that down to a finite number of cycles. And that's a pretty dramatic difference.
Yeah, and it really highlights why engineers need to be so precise. With their calculations and the materials they're choosing, the design has to match the way that slab is going to be used.
So how do they figure out how thick these slabs need to be in the first place? There seems to be a couple of ways to approach this whole thing. I mean, our source mentions things like axle loads and contact areas, and then there are all these different calculation methods.
Right. There are multiple tools in the toolbox, and each has its own strengths and weaknesses. You've got some simpler methods like using charts. From organizations like PCA, And those are great for common situations, Like if you're designing a slab for a single axle load, but then there's the more complex stuff, like the finite element analysis. That's like bringing out the big guns for those really complex, really intricate projects.
Okay, so that covers unreinforced SOG. But remember that hint earlier about fibers. Let's shift gears and talk about fiber-reinforced SOG.
Now we're talking. Fiber reinforcement is a game changer when it comes to SOG design. And here's the thing. Fibers aren't about preventing cracks altogether. They're about controlling those cracks. Like, they act like little tiny bridges, holding that concrete together even when it cracks, and that gives it what's called residual strength.
So it's less about eliminating cracks and more about managing them, like a strategic surrender. It's kind of cool. Now, I am curious about the types of fibers that are used in SOG. Our source mentions both steel and synthetic macro fibers. What's the difference? And why would you use one versus the other?
Good question. So steel fibers are like the heavy lifters when it comes to strength after the concrete cracks. Post-crack strength, that's what we call it. They provide that extra oomph to hold the slab together even after it cracks. Synthetic macrofibers, on the other hand, they're masters of shrinkage control. They're like little tiny nets that distribute the stress and prevent those wide cracks that can sometimes form. And then, of course, you can also combine the two. You get the best of both worlds.
It's like having a superhero team for your concrete, each with its own special powers.
Exactly. And choosing the right combination is key in the design.
Okay, so we've got these fibers working their magic. But how do engineers actually design these fiber-reinforced slabs? I feel like that's the real nitty-gritty that people want to know about.
Absolutely. There are three main design methods for fiber-reinforced SOG. The elastic method, the yield line method, and then nonlinear finite element modeling. Each has its own advantages and complexities.
Okay, break it down. What's the difference?
All right, so the elastic method is the most straightforward one. It basically modifies the allowable stress calculation to factor in that extra strength from the fibers. Think of it as like boosting the concrete's natural strength.
So like a fiber-powered boost.
Exactly. Now, the yield line method, that one gets a little more complex. It considers how the slabs can behave under really heavy loads and takes into account things like plastic hinges. So imagine bending a metal ruler. At some point, it starts to bend permanently, right? That's a hinge. The yield line method accounts for that kind of behavior in the slab. But for this method to work, the fibers have to be tough enough to hold that concrete together, even when it's undergoing those large deformations.
And lastly, nonlinear finite element modeling. That just sounds super complex.
That's the most sophisticated one. And it's very computationally intensive. So it's like creating a virtual model of the slab and then subjecting it to all sorts of things. Shrinkage, curling, variations in the soil underneath, everything. It's a super powerful tool, but often only used for really, really complex projects where accuracy is, super important.
So it's like they've created their own virtual testing lab.
Exactly. And choosing the right design method. Well, it all depends on how complex a project is and how much precision is required. Sometimes a simpler method is enough. But for those really challenging projects, the advanced methods are invaluable.
Now, let's shift gears slightly and talk about reinforced SOG in general, not just the fiber-reinforced kind. We've been focused on fibers specifically, but there are other ways to reinforce these slabs, right?
Right, and this is important. Reinforcement, whether it's fibers, steel bars, whatever, it doesn't eliminate cracks entirely. It's about managing them.
Working with them.
Yeah, precisely. Reinforcement in SOG has three main purposes. Limiting how wide those shrinkage cracks get, allowing for longer spacing between joints, and providing strength at the sections where cracks do occur.
So it's not about creating a perfectly crack-free slab. It's about making sure those cracks don't cause problems.
Exactly. And that's something engineers need to talk about with building owners. Cracks in a SOG aren't always a sign of failure. It's just how concrete behaves. Managing expectations, making sure everybody understands the material.
That's a good point. Well, we've covered a lot of ground here, from the basic definition of SOG to the complexity of reinforcement crack management, but there's still more to explore. Before we move on, I want to take a look at this real-world example that's in our source material, featuring an SOG design that has to handle some pretty heavy loads. Crane loads, actually. And they use that Egyptian code that we were just talking about. And what really stood out to me here was how complex this scenario is. I mean, they're dealing with a large panel, no reinforcement, but using a minimum amount of fiber-reinforced concrete to handle the shrinkage stress. Plus, there's this specific soil involved and a higher concrete strength. Lots to consider.
Yeah, It's a perfect illustration of how all those concepts we've talked about come together in a real project. You've got the size of that panel, the weight of the crane, the concrete strength, even the soil underneath, and it all influences the design decisions. They even mention using special software to help them calculate the stresses, because things can get pretty complex.
Yeah, it definitely sounds like it. They actually calculate the modulus of rupture for this particular scenario, which, if you remember, tells us how much bending stress that concrete can handle before it cracks. And they get a value, but then they point out that the maximum stresses from that crane actually exceed that value. Does that mean the slab is going to fail? I'm going to get a little worried just thinking about it.
No, don't worry. Just because you exceed the modulus of rupture doesn't automatically mean the slab's going to fail. What it means is the slab will likely crack under those heavy loads. But that's where the fiber reinforcement comes into play, remember?
Right, the fibers, I forgot about that. So the fibers are there to kind of control those cracks, make sure they don't turn into something catastrophic.
Yeah, exactly. It's a great example of how fiber reinforcement allows engineers to kind of push the limits. You can design for heavier loads, larger panels, without just having to make the slab thicker.
Interesting. The source material also dives into all these different loading scenarios, like what happens when the crane wheels are in the middle of the panel, at the edge, at a corner. Seems like where that load sits makes a big difference.
It makes a huge difference. The location of the load is critical. The stresses in that slab aren't going to be uniform. They're concentrated under that load. And engineers have to consider those possibilities, you know, the worst case scenarios, to make sure that the slab is strong enough. It's all about anticipating, designing for those critical points.
It's amazing how much engineering goes into something that looks as simple as a flat piece of concrete. Like a whole world of forces and calculations.
It is. It really is. And that's part of what makes engineering so fascinating, understanding all those unseen forces and then designing structures that can stand up to them safely, efficiently.
Now, speaking of design elements, let's talk about shrinkage joints. Those seem to be super important for SOG construction, but I'm not really sure why they're needed. What's the deal with those?
Think of them as planned cracks. They give the concrete space to shrink as it dries without causing those random cracks, the kind that can weaken the slab.
Okay, so it's like giving the concrete a little breathing room.
That's a good way to put it, because as concrete cures, it loses water and shrinks. And if it doesn't have anywhere to go, you get all these stresses building up. That's what causes those uncontrolled cracks. Shrinkage joints relieve those stresses so it shrinks predictably.
Makes sense. But how do they know where to put those joints? How far apart?
Well, there's no simple answer. Spacing depends on a few things. The type of concrete, the weather, how much reinforcement is used, even the shape of the slab.
So there's no magic formula?
Nope. It takes judgment, experience to get it right. Engineers use their knowledge, the guidelines, the codes to figure out the best approach for the project.
Sounds like there's a bit of art as well as science to SOG design. It's not just plugging in numbers. You have to understand how concrete behaves and factor in the conditions of the project.
That's it. Engineering is both. We have our scientific principles, but there's definitely intuition, experience that comes into making those tough design choices.
And speaking of experience, what about the long-term performance? How do these slabs hold up with all those loads and exposure to the weather and everything?
Durability is a big deal for SOG. Engineers are going to select materials and construction methods that'll last. Things like the concrete mix, proper curing, making sure the concrete gets strong, using the right type of reinforcement, all those are important.
They put a lot of thought into making sure these things are built to last, huh? Our source material didn't really get into maintenance, but I'm guessing regular checkups, maybe some minor repairs are important too.
Oh yeah, absolutely. Like anything else, SOGs benefit from being looked after. Sealing cracks if they pop up, making sure water drains away properly, even just keeping it clean. Small things can make a big difference.
It really is fascinating how much goes into something as simple as a concrete slab. We totally take them for granted.
For sure. It's really a testament to how creative engineers are. They're always working to improve the world around us and how they use their knowledge to do that.
Okay, before we wrap up, I want to go back to something we mentioned earlier. The relationship between the design, the building codes, and then the real-world applications. It's like a constant balancing act.
You got it. Codes are there for safety, for reliability, but they don't tell you everything. Engineers got to interpret those codes, use their judgment, figure out the constraints of the project, then come up with the best solution.
So it's not just about following the rules. It's about understanding why those rules exist.
And that's where experience comes in.
Yeah.
And knowing the principles behind everything, it's about seeing the big picture and coming up with solutions that work for that specific project.
Like a puzzle, you got all the pieces, the codes, the materials, the loads, and you got to figure out how to make it all fit together to get a safe, durable structure.
That's a good way to put it. And that's what makes engineering so cool. Finding the solutions, making the world better.
Now, I got to ask about sustainability. There's a big push to use recycled materials, be more environmentally friendly. How's that changing the SOG world? Seems like the perfect place to use those ideas.
Great question. And it's definitely on everyone's minds. We're seeing a lot more recycled aggregates used in concrete, which is awesome. It reduces waste. And we're not using as much brand new material. But there are some things to think about, especially when it comes to how well the material performs and how long it'll last.
It's not just a simple swap then.
Right. Engineers need to figure out how those recycled materials might affect the concrete, the strength, the shrinkage, the durability. And that takes research and testing and a willingness to, adapt our designs to use these materials in the right way.
It sounds like SOG is constantly changing. New tech, new materials, sustainability. Exciting times.
It is always evolving. It takes innovation, pushing those boundaries, and who knows what the future holds. Maybe we'll have self-healing concrete someday, or slabs with sensors built in.
Sounds like there's a whole lot more to learn about sustainable SOG. Maybe that's a future deep dive.
I'd love that. It's a field that's ripe for innovation.
Well, it sounds like we've only just scratched the surface when it comes to sustainable SOG. Definitely something to keep our eyes on. But for now, let's wrap up this deep dive. We've covered a lot today. Different types of SOG, designing unreinforced versus reinforced, all that fiber reinforcement stuff.
We did pack it all in.
If you had to pick like a few key takeaways, what would they be? What do people really need to remember?
Well, first off, SOG construction. It's a lot more complex than it looks. There's so much engineering that goes into designing these slabs to make sure they can hold the weight, withstand the elements, last a long time.
It's more than just pouring some concrete, that's for sure.
Way more. You got to think about the soil, how the slab's going to be used, what kind of loads it'll see, and then you pick the right design, the reinforcement. It's a whole process.
And those cracks, managing those cracks, super important.
Yeah, it's not about getting rid of them completely. It's about making sure they don't mess things up. The slab's got to do its job.
Right. And we saw how different building codes, like that Egyptian code we talked about, can offer some different perspectives on the whole SOG design thing.
That's true. It's good to see how engineers in different parts of the world approach these things, learn from each other.
And we got a little peek into the future of SOG with sustainability.
Definitely a big trend. Recycled materials, being eco-friendly, it's shaping the future of SOG design.
Yeah, I got to say, I have a whole new appreciation for these concrete slabs now. They're pretty amazing when you think about it.
I agree. It shows how creative engineers can be, using their knowledge to improve things.
Before we go, I want to leave everyone with one last thing to think about. We talk about using recycled materials in concrete, but what about other stuff that's coming? How will things like new materials, sensors, maybe even AI, how will all that change SOG in the future?
Ooh, that's a good one. Imagine concrete that can heal itself, or sensors that tell you if something's wrong before it becomes a big problem. It's going to be interesting to see what happens. It's an exciting field.
I can't wait to see what's next. Thanks for joining us on this deep dive into slab-on-ground construction. Hope you learned something new, and maybe you see those concrete slabs a little differently now. Until next time, keep exploring, keep learning.